In section 1.4, we discussed functions. So a function is going to be defined as, we say that a function f from a to b is a relation that assigns each element x in your first set A to exactly one element, which we call f of x, in the set B. So you should think about a function as a map that takes all of the elements in one particular set A and sends each element somewhere in another set B. That first set A, that's our set of inputs, is called the domain of the function. In B, the set of potential outputs is called the codomain of the function. We don't want to get that confused with the actual outputs of the function, which is called the range of f. So I've drawn a diagram, or a map, of a particular function here. Alright, so these arrows are representing where f is sending each element in A to where that element is being mapped to in B. Alright, so we would say that because the element 1 in A is mapping to the element little a in the set B, we would write that f of 1 is equal to A. That's what this notation means. It means this function f is mapping the element 1 to the element little a. We would also have f of 2 is equal to C, because the element 2, if you follow the arrow along, ends at the element C. And similarly, f of 3 is also equal to C, because element 3 gets mapped here to C. Alright, now what is the domain of this function? What is the range and what is the codomain? Well, the domain and the codomain are often given to you, or you can determine them based on the context of the problem. But for us, we can see that the domain is given to you as the set capital A, and all of it consists of is the elements 1, 2, and 3. That's the domain of f. And B is also given to you, that's the set of potential outputs, and we can see that the potential outputs are the elements little a, little b, and little c. So we call that the codomain of the function f. We don't want to get that confused with the range of f, because the range of f is the actual outputs of the function. In other words, it's the elements of B that are getting mapped to by something in A. So the range of this function, we can see the possible, or the actual outputs that you get are A, C, and then C again. Right? We don't need to write C twice. So we would just say that the range of f is going to be the set consisting of A and C. Those are the only elements in the codomain that actually get mapped to under this function. So we always want to think about a function as being some kind of a map that takes each element of one set and sends it somewhere in another set. Those two sets could have overlapping elements, they could have some elements in common, they could have all elements in common. Alright, but it has to be the case that every element of the domain maps to somewhere in the codomain. So some things to notice about this definition. Let me zoom in for a second. First of all, every element of A, that's the domain, has to go somewhere in B. It can't be mapped to something outside of B, and it can't be undefined. Second, not every element of B needs to get mapped to. If we go back to our example on the last page, we had that element little b in the codomain and nothing mapped to it. That's okay, that's allowed. Right? It could be that your codomain has more elements than the actual output of the function. That's fine. You can have different elements of A getting mapped to the same output. That's allowed as well. Right? The outputs of each element in the domain don't necessarily have to be unique. Again, if we go back to this last example, both 2 and 3 are getting mapped to the element C. You're allowed to have multiple elements of the domain mapping to the same element of the codomain. However, you cannot have a single element of A mapping to two separate outputs in B. That's not allowed because, again, your function won't be well defined. Remember, this function is a map. It's telling every element of A exactly where to go in B. So if it's telling an element of A to go to two separate places in B, it's not a very good map, right? You need to be telling each element of A exactly what single output it has to go to in B. So let's look at these 3 maps. Oh, nope, that's 4. Let's look at these 4 maps that I've drawn and try to determine which of these represent functions and which do not. So in the first case, is this a function? You might want to pause it and convince yourself one way or the other. But this is not a function. Whoops, sorry. Oh boy. Let's try it again. not a function. It's violating that first note that I wrote above. Every element of A has to be mapped somewhere. The problem is I have the element 2 in the set A, and it's not getting mapped to anything, right? F of 2 is undefined. That makes this map not a function. Now in this second map here, is this a function? Yeah, this is fine. This looks similar to the one we saw in the first example. Every element of A goes to somewhere in B, and it's not the case that any element of A goes to 2 separate outputs. So this is a function. All right, how about our third example here? We have every element of A is mapping somewhere in, it looks like our codomain is now called X. That's allowed, right? We're allowed to have multiple elements of A getting mapped to the same element of the codomain. That's fine. So this is a function. But this last example here, this is not a function. And that's because the element 1 has 2 different outputs. So this is violating that fourth note from up above. You can't have a single element of A mapping to 2 separate outputs. This is saying that f of 1 is equal to A, but it's also equal to B. That's not allowed. You can't have a function or mapping a single element of the domain to 2 different elements of the codomain. That's bad. So this is not a function. All right, now we used a diagram to look at a few examples before, but a diagram is not really a reasonable way to describe a function if your sets, if your domain and your codomain are infinite. And so oftentimes we can use an equation to describe the relationship between inputs and outputs. As an example, consider the function f from R to R. If you're not familiar with this notation, this is saying that the domain is R, which is the set of all real numbers. And it's saying that the codomain is also going to be equal to R. So it's this is a function that's taking a real number and it's mapping it to some other real number. So the codomain and the domain are both the set of real numbers. But we're going to define this rule by saying f of x is always equal to 1 minus x squared. All right? So if we wanted to draw a picture of something like that, we could try to get an idea by doing something like, all right, here's R, that's my domain, and here's my codomain, which is also R. Now let's think about where this function would send some key elements of the domain. All right, well, where would this function send 0? Let's think it through. F of 0 is going to be equal to 1 minus 0 squared, which is just 1 minus 0, which is 1. So this is going to end up getting mapped to the real number 1. Where's 1 going to get mapped to? Well, f of 1 is going to be defined as 1 minus 1 squared. That is 1 minus 1, which is 0. So 1 is going to get mapped to the element 0. All right, where's negative 2 going to get mapped to? F of negative 2 should be equal to 1 minus negative 2 squared. That is 1 minus negative 2 squared would be 4. And 1 minus 4 is equal to negative 3. So 2 is going to get mapped to negative 3. The problem is we can't do this forever. We've already missed a lot of real numbers. There's a lot of real numbers between 0 and 1. There's a lot of real numbers between 1 and negative 2. We can't really draw a diagram to represent the whole thing, but we can at least choose some, right? We can pick out some particular values of the domain and see what we get as outputs. Now, we'd like to have a better idea of what each element of the domain is getting mapped to, and we can't really do this infinitely many times, but what we can do is we can consider the set of all ordered pairs of the form some x value, where x is a real number, and then whatever the output is, f of x. And so, for example, we could look at the ordered pair 0, 1. When we have an input of 0, we get an output of 1. So 0, 1. Or we could look at the ordered pair 1, 0, because when we input 1, we got an output of 0. we can look at the ordered pair -2, -3. Because when we input -2, we got an output of -3. If you looked at every single possible ordered pair for every single possible real number x, it's going to give you a graph in the Cartesian plane, which is going to describe every possible input and output of this function. All right, so we'll get to the graph in the next section. All right, but notice what we did here was, in order to find these ordered pairs, we took a bunch of different possible inputs, right, different possible domain values, and plugged them into that function, replacing x with that particular input. We call that evaluating a function. So to evaluate a function means to replace a general input x with a specific number that's in the domain, or some other variable or some other expression. So let's look at a couple more examples of that, because we've already evaluated the function f at various real numbers, but we can also evaluate a function at different variables and expressions. So as an example, consider the function g of x, which is defined to be -x² plus 4x plus 1. That means when you input x into this function g, your output is going to be -x² plus 4x plus 1. So to evaluate g of x at 2, what we need to do is we need to replace each instance of x with a 2. All right, so that means I need to rewrite this equation here, but replace my x's with 2. So this is going to look like -2² plus 4 times 2 plus 1. So everywhere I saw an x, I just put parentheses around it and replaced it with a 2. Now, to actually evaluate this and get a number, I need to make sure that I do my exponents before I multiply by that negative, right? Because in our order of operations, exponents comes before multiplication by a negative. So this is the opposite of 2², the opposite of 4. Plus 4 times 2 is 8, plus 1. So this is going to be 4 plus 1, which is 5. So when we evaluated g of 2, we got 5. That means 2 is going to get mapped to 5. Right, but we don't always have to evaluate at a particular value. We can evaluate g of t by replacing each instance of x. Instead of replacing it with a 2, now we're going to replace it with a t. So just go through your original equation here, replace each instance of x with t. You'll get that g of t is equal to -t² plus 4t plus 1. And finally, if I wanted to evaluate the function g at the value h plus 2, that means I need to replace each instance of x with the expression h plus 2. All right, so let's see what that looks like. That's going to look like -h plus 2² plus 4 h plus 2, I should have put parentheses around here, plus 1. All right, so all I've done is gone through my g of x, and I've replaced each instance of x with h plus 2. Now, it might be useful to us, depending on the context, to simplify this expression even further. To do that, I would need to use the distributive property twice here. First of all, leave the negative on the outside alone and square h plus 2 first. So this is -h plus 2 times h plus 2 plus 4 times h plus 2 plus 1. That's going to give me, when I distribute this out here, use FOIL, use the distributive property. Inside the parentheses, you'll have h² plus 4h plus 4. Then if I distribute 4 times h plus 2 here, I'll have 4 times h, which is 4h, and I'll have 4 times 2, which is 8. And finally, at the end, we have a plus 1. Right. And now, distributing this negative sign, I need to change all the signs inside the parentheses, so this will be -h² minus 4h minus 4 plus 4h plus 8 plus 1. And if I simplify all of this, well, -4h and +4h will cancel each other out, and then I just need to combine my constant terms. So I end up with -h². -4 plus 8 would be 4, plus 1 is 5. So I get -h² plus 5. Okay. Now other types of functions sometimes a function isn't going to have a single equation that describes what the output is depending on the input. Sometimes the output is going to change depending on which input you choose. In other words, sometimes for a certain subset of the domain, you'll use a certain equation, and for a different part of the domain, you use a different equation. We call such a function a piecewise function. So if f of x is the piecewise function where f of x is equal to x squared plus 2 for x values that are less than 0, and f of x is equal to x minus 1 for x values that are greater than or equal to 0, this works similar to the functions we saw before. It's just we're going to break up the domain into two separate parts, right? So they didn't tell us the domain here, but this function is defined for all real numbers. So our domain is all real numbers. And they're showing us that it's broken up based on the x values that are less than 0. That is everything from negative infinity to 0 is going to use this first rule of x squared plus 1. And then for any x value greater than or equal to 0, that is from 0 to infinity, we're going to use that second rule. I'm just going to highlight this just to make sure we're clear on how this works. So we're going to use this function rule when our x values are less than 0. And then we're going to use this function rule when our x values are greater than or equal to 0. So for this part of the real number line. All right, let's use that to try and evaluate this function at a few values. Let's say we want to find f of negative 5. Well, our input, our x value here is negative 5, and negative 5 lies over here, right? In other words, negative 5 is less than 0. So we're falling into this first category here where f of x is equal to x squared plus 1. So to evaluate this, I need to plug it into the function x squared plus 1. So we have negative 5 squared plus 1. That is 25 plus 1, which is 26. Now f of 3, at this point, my input, my x value is 3, which is greater than or equal to 0, right? 3 definitely falls into the blue part of my domain because it's greater than or equal to 0. So to find f of 3, I need to use the second function rule, x minus 1. So f of 3 is going to be equal to 3 minus 1, which is equal to 2. Now what about f of 0? Which one of these two parts of the domain does 0 fall into? Well, 0 is not less than 0, but it is greater than or equal to 0, which means our input here falls into that second category, right? Our x value is greater than or equal to 0 because our x value is 0. 0 is greater than or equal to 0, which means we're going to use that second function rule again and get that f of 0 is equal to 0 minus 1, because we're using this function rule here, which is negative 1. Okay, now piecewise functions are used all the time. For example, anytime you have like a phone plan, that's probably going to be piecewise. They charge you some particular rate up to a certain level of data, and if you go over that, you have to pay some amount based on how much you go over. This is a piecewise function because depending on how much data you use, they use a different rule to compute how much they're going to charge you, right? But piecewise functions come up in other contexts as well. All right, we're going to very briefly talk about graphs of functions because we had started talking about it earlier, and we'll continue this in the next video. The graph of a function is just a set of all ordered pairs of the form x, y, where y is equal to the output of the function when we have an input of x. That is, if an input of x gives you an output of y, then we're going to have the ordered pair x comma y in our graph. So if this is a graph of our function, I just sketched it here in green, and we have some point x comma y on the curve, what that means is that f of x is equal to y. When you input the point x, you get an output of y. All right, to give you a concrete example, if this is the point, whoops, don't do that. If this is the point 1 comma 4, that means for this function, f of 1 is equal to 4. If you input 1, you get an output of 4. So the graph is just a set of all possible ordered pairs of inputs and their associated outputs. So let's look at an example of how we can try to sketch a graph of a function. So suppose we have the function f of x is equal to x squared plus 1. We're going to try to get a sense of what this looks like just by plotting some points. So let me start off by trying to evaluate this function at some x values. I'm going to start at negative 2. So f of negative 2 remember how we evaluate this. Replace every instance of x with 2. This is going to be negative 2 squared plus 1. That's 4 plus 1, which is 5. Now let's evaluate it at negative 1. That's going to be negative 1 squared plus 1. That's 1 plus 1, which is 2. F of 0 is going to be 0 squared plus 1. That's 0 plus 1, which is 1. F of positive 1 is going to be positive 1 squared plus 1, which is, again, going to give you an output of 2. And finally, f of 2 is going to be 2 squared plus 1, which is 4 plus 1, which is 5. All right, now remember, our inputs, comma, outputs are going to be points that are going to be on our graph. So negative 2, comma 5 is going to be a point, an ordered pair on our graph. Similarly, negative 1, comma 2 is going to be on our graph. 0, comma 1, 1, comma 2, and 2, comma 5. Right? If I plot all those points, I'm going to get something like this. 1, 2, 3, 4, 5. I get a point at negative 2, 5, at 1, comma 2, 0, comma 1, 1, comma 2, 2, comma 5. And so this graph ends up looking something like this, roughly. All right, now sometimes it's harder than others to know exactly what their graph looks like, but I happen to know that an x squared function is a parabola, so I was able to sketch that in there. All right, now, an important thing to realize is that all functions are given by equations, but not all equations will represent a function. Similarly, if you have an equation, you can find its associated graph, and we can use that graph to help us determine whether that equation represents a function. Right? Remember, functions have particular rules, and one special rule is that any particular input, any particular x value, can only have one output, can only have one associated y value. So we can use the vertical line test to help us determine whether a graph is a graph of a function or not. All right, now the vertical line test says a curve in the Cartesian plane is the graph of a function, spelled that wrong, if and only if no vertical line intersects the curve in more than one point. That is, if you can draw a vertical line anywhere in the Cartesian plane and it hits your curve in more than one spot, it's not a function. Now, can you draw a vertical line anywhere in this first graph and hit the curve in more than one spot? Yeah, sure, there's lots of places you could, right here, for instance, or here, right? Many places where you could draw a vertical line, but you really only need one. So as long as there's one vertical line you can draw that intersects a curve in two places, this fails the vertical line test. And it fails the vertical line test because we have a particular x value with two possible y values. That is, the input x gives you two possible outputs. That's not allowed in a function. In a function, any input needs to give you just one output. So this is not a function. All right, what about the second graph here? Well, let's try to draw some vertical lines. This only hits the curve once, this only hits the curve once. Imagine just moving your pencil all the way across this graph, drawing a whole bunch of different vertical lines. It never hits the curve in more than one spot. So this passes the vertical line test, which means this is a function. All right, how about this third graph here? Is there anywhere you could draw a red line where it hits the curve in two spots, and at least two spots? Well, over here, no. This looks like it's only intersecting the curve once, but once you hit this part here, there is a place where a vertical line hits the curve in more than one spot. So for that vertical line, because we're intersecting the curve in more than one point, this is going to fail the vertical line test, which means this graph does not represent a function. Right? And finally, this last graph here, this looks like a graph of a piecewise function that we were talking about before, because it gives you a particular graph for a little while and then it changes to a different graph. So if we imagine drawing a whole bunch of red lines through here, it doesn't seem to intersect a graph in more than one spot. The only potential issue could be right here, where your rule switches, right, where you switch from one line to another. But because we have an open circle here, we highlight it, because this is an open circle, that's saying that's not actually the output of the function. There's only one output of the function, and it's down here where we have a filled in hole. So this does not fail the vertical line test. This actually passes the vertical line test. So this is a function. If both of those circles had been filled in, well, then it would have failed the vertical line test, and then it would not be a function. Right, one last example. Remember that x squared plus y squared equals 1 has a graph of a circle? We talked about that in a previous video. Is that a function? Well, we could pretty quickly see that it's not using the vertical line test. Let's say this is our graph here. It's a circle with a radius of 1. It's not, right? You could draw a vertical line here. It's going to intersect the graph in 2 different points. To give you a specific example of why it's not, though, consider the x value of 0. Oops, for x equals 0, what would the output of this function be? Well, we need to have 0 squared plus y squared equal to 1. Well, 0 squared is just 0, so this is really y squared equals 1. And so y could have 2 possible outputs, positive 1 and negative 1. That is, we have points 0, positive 1, and 0, negative 1, both as points on this curve, which means it's not a function because a particular input of x, namely x equals 0, gives you 2 different outputs of y, positive 1 and negative 1. So this is not a function. We'll continue talking about graphs of functions in the next video.